introduce
Okay,
you and
sounds good.
give it. Thank you, sir. Yeah, please,
Thank you.
Pujita or Sri Sai Krishna, please proceed.
Yes, sir. Yes, sir. It's great to have you all back again. Now, let's have a keynote talk titled Development of Sustainable Flexible Pavements by Asphalt Replacement. And I would like to introduce the eminent speaker, Dr. Ramesh Hasgaru. Dr. Ramesh has obtained his bachelor's in civil engineering with a minor in engineering science and mechanics from Virginia Tech in 2014. He completed his master's in 2016 and PhD in 2019 in civil engineering at the University of Texas at Austin. Dr. Ramesh is working as an assistant professor in the Department of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign. Dr. Ramesh led the role of a senior research scientist of the Search Committee of Illinois Center for Transportation in 2020 and currently serving as a research engineer of the Search Committee of Illinois, Swiss National Science Foundation, external grant reviewer of Research Grants Council of Hong Kong. Dr. Haas is a technical reviewer for construction and building materials, mechanics of materials, transportation geotechnics, International Journal of Pavement Engineering, road materials and pavement design, materials and structures, and many more. Also, he is a member of the Transportation Research Board, Academics, National Academics of Science, Engineering, and Medicine, Academy of Pavement Science and Engineering, American Society of Civil Engineers, Engineering Mechanics Institute, and Association of Asphalt Paving Technologies. To date, he has published in a wide range of peer-reviewed journals and presented his work at many international conferences. Currently, Dr. Ramesh's research is funded by the Illinois Department of Transportation, the Smart Transportation Infrastructure Initiative, the Indiana Sea Grant, and numerous industry partners. His research focuses on asphalt binders, mixtures, pavements, and also on areas of viscoelasticity, composites, machine learning, and computational modeling. Hereby, I would like to thank Dr. Ramesh Hasgaru for his constant collaboration with us, and I take this privilege to hand over this session to you, sir.
Okay, should I go ahead and get started?
Yeah, please proceed, sir.
Okay, so thank you so much for the opportunity. I'm just going to go ahead and share my screen. Okay, that's fine. I think there is some issue here. Sorry, there seems to be some issue sharing my screen. I think it's okay. Okay, are you able to see my screen yet?
We are able to see the screen, sir. Yeah.
You are able. Okay, so I will go ahead and get started. There we go. Okay, so again, thank you so much for the opportunity to present here. And it's working, it's in the full screen now?
Full screen, sir. Yes, sir. Please proceed.
Okay. Yeah, sorry about that. I'm not so used to Teams. That's new for me. So thanks everybody. And again, sorry for the delay. I had some some issues connecting to the call earlier. So now I'm here in my office and seems to be working well. So thank you everybody. Today I'm going to jump right in and talk about some of the sustainable practices for asphalt replacement, and maybe I want to give some indication for the students here what might be relevant specifically for India, because I know most students are going to go on to work as practitioners in this field or closely related fields, and need to know kind of what's relevant for them as we move into this new frontier of sustainability. So pavement engineering, I always like to start with this slide because it reminds us, in the past, we focused so much on predicting asphalt distresses. And what do we mean by distresses? We mean rutting, this kind of deformation of the road, and cracking, as you see here. So we always focus on predicting these stresses in the past so that we can choose the right materials. Now, in the future, we're going to move to designing better materials through engineering based on fundamental concepts and computational techniques that we can use. This will help us to have a longer pavement life, use more recycled materials, reduce CO2 emissions, and incorporate some smart technologies. So first, I want to start off talking about what is asphalt binder, because actually asphalt binder is the part we're trying to replace. Asphalt binder is the binding agent. It's the glue that holds aggregates together. We are also trying to replace aggregates, but not quite as much as the binder. It's obtained from fractional distillation of crude oil. So this basically means it's coming from the oil and gas industry, but it can also occur naturally. That's a very small amount. Almost all is coming from oil and gas industry. So you can see why we are, of course, trying to replace it quickly. It's got a complex hydrocarbon structure. So again, this is related to the fact that it's coming from petroleum industry. It's made up of hydrocarbons, if you remember from your chemistry class, and essentially it's the heavier kind of fractions, higher molecular weight, and the leftover stuff that cannot be used as fuel for vehicles and whatnot. So it's the leftover stuff. It's being used as, of course, asphalt, but it's not free. It's not a waste material. It's something we are getting from the petroleum industry, but it's still expensive and it's still taking some difficulties to use. It's a thermoviscoelastic material, which most of you at the undergrad level probably are not too familiar with materials with this property, but basically this means it's very sensitive not only to temperature, but also to the loading rate at which the material is applied. So it's very sensitive to the rate at which we load the specimen, meaning the traffic speed in our case, because we're talking about pavements. And all sources, even different batches from the same source, have different properties. So you will see the properties look a little bit different from each source. And sometimes even the same producer will hand you asphalt binder in just a few different weeks apart, and you will see that there's some big differences. So we try to think of this material always as being very dynamic. We don't know exactly what we're getting at any time, but it's important to characterize it because it's generally thought to control mixture cracking. So for a long time, we studied just the regular binder, right? Just the asphalt binder coming from petroleum sources. But as mentioned, there are some new challenges now. And one of the biggest challenges is that we aren't going to have asphalt binder the way we did, right? On top of that, there is a lot of push to be more sustainable, right? To reduce our carbon footprint. So we need to use asphalt in a strategic way where we're using recycled materials, rejuvenating the materials we have, and then replacing asphalt. And again, I want to focus this presentation a little bit on what's relevant maybe for you guys, for those watching at home, so that they can understand, what might help improve infrastructure in India, but also infrastructure around the world to make our time using this material a little bit more sustainable. So first I want to talk about recycled asphalt. So reclaimed or recycled asphalt pavement is, in the US, we reclaim 90 million tons of asphalt a year. And 80% of that is recycled, meaning that this is the most recycled material in America. And a lot of people are not thinking about this material specifically. They're thinking about recycling, the materials we recycle at home, metals and plastics and whatnot. But actually, this is the most recycled material on Earth. So we recycle so much, we save $30 to $80 a ton when we recycle. But more important, this practice should be green. It should be sustainable. Now, the recycling today is not as relevant in India because, of course, many of the asphalt pavements are newer, right? India was previously using a lot of concrete for paving of roads and now is having many more miles than previously were paved, right? So a lot of this recycling is not so relevant because there are not so many pavements at the end of their service life right now in India. But it will quickly become relevant as more pavements reach the end of their life and you need to decide what to do with those materials. Because if you send them to the landfill, you're totally wasting those potential of recycled materials, and also you're creating waste, right? So instead, we try to recycle as much asphalt as we can for the pavement. We can also recycle materials from asphalt roofs. So in America, we have a lot of asphalt roofs that we need to we can reclaim that roofing material at the end of its life, use that in the pavement, but it poses a lot of challenges, as you'll see. So just to give you an idea, as I mentioned, we recycle 80% of 90 million tons, so that's roughly 72 million tons. And for municipal solid waste in 2017, all of it together was 67 million tons. So again, asphalt is more than all of the municipal, meaning the things from houses and kind of regular businesses. Asphalt is more than all of that we're recycling, right? So we're recycling such a huge amount. This is the challenge, right? We want to use this material as a replacement for the asphalt we're already using. But the major challenge is this material compatible with the virgin asphalt? So is the wrap binder in the asphalt mobilized? And do the different wrap and virgin binders blend differently, right? The wrap binder is heavily oxidized. It's more stiff. And it has a difficulty mobilizing because this material is aged, right? So that means it had some reaction with the oxygen, and now it's finding a lot of difficulty getting it to move again at normal mixing temperatures. And the big challenge here from sustainability perspective, so I think I talked about this last time, but I want to now emphasize the sustainability perspective, right? The big challenge from sustainability perspective with this mixing is if we have to raise the temperature to mix it, that increases CO2 emissions and it increases hazards to human health, right? Those are the two things we cannot have. We cannot, when we use wrap, maybe we reduce the CO2 emissions because we need to produce less binder, but then we're increasing them again when we use it because we're raising the mixing temperature, right? This is a big challenge. This is something we cannot do. So we don't want to elevate the temperature. We want to keep the temperature reduced. And so maybe not all wrap binders can be, not all wrap binders can be used the same way. So we have to consider which ones to use. And again, I think I showed this last time, but we came with some simple procedure, titration-based procedure. We want to indicate, is this material suitable for recycling? So we have some titration-based procedure where we check the dispersive forces present using titration of a solvent. So we just add drop by drop of solvent to a sample of binder, and we measure how much dispersive force is present. So if the binder is too stiff and brittle to be mobilized, we get a good sense of that and we can know to avoid that wrap or to use it in a different application. You can see just some different binders, so some different virgin asphalt binder compared with wrap. So we have some baseline, and then some wraps are almost exactly the same, so they haven't been aged at all, and some are very different. So again, I wanted to present this work again because I feel that this is so crucial as it comes now a challenge in many countries to use wrap for the first time, right? Not to make the same mistakes that we have in the United States where we just said all wrap is treated equally. Instead, we want to make sure we're screening the wrap properly and understanding how we can use this material for the first time. And I think if you guys, when you go into industry, many of the students here will find there's always a challenge like to save money, right? So the contractor needs to save money. They want to do the most efficient. They want to use the most wrap possible because it's free. It's a waste material. But what you will find is that you need to check carefully if this wrap can be used and if it's going to lead to premature distress. Because a lot of times when the construction is over, the contractor is not responsible anymore. Then it becomes the agency's problem. So if you are working for the highway agency, you want to make sure that you're stressing that you need to check if that wrap is good. And this is something we're still not doing in the United States today. So we're still a little bit concerned about if all wrap is equal, right? Next thing, we want to check the interaction between the base binder and two different wrap samples. So this was also done in this study, right? We checked the dispersive forces present in mixes of wrap and base binder. And again, that's another way to identify which wrap is more prone to recycling and better wrap blends with specific virgin binders. So compatibility is important. I suggest definitely to keep the compatibility in mind as you explore this material. So now let's talk about rejuvenation. If you have wrap that's incompatible, you still need to use it, right? This is the most critical thing. Maybe you'll have wrap that you simply cannot, you don't know how to use, but you cannot landfill it, right? So maybe we can rejuvenate. And I just wanted to talk very briefly some of the types of rejuvenators. A lot of the current best ones on the market are proprietary. Meaning that these have some commercial formulation. Some company has created them and decided this will be the best softening material to bring the stiffness down and reuse in construction at a reasonable temperature, right? So to avoid the CO2 emission, to make it more sustainable. But from the biomaterials perspective, this presents a really nice option. Actually, I think this is becoming quite popular in many parts of the world because these first ones, proprietary, are quite expensive, but biomaterials can be obtained for cheap or even for free coming from nature. So you can have waste from animals, waste from plants, oils that are available, things like that, right? There's also high malting oils that come from petroleum industry, similar process to asphalt. And there's recycled oils such as even cooking oil. We published one paper recently on using the waste cooking oil. Some people also use the waste engine oil. So this kind of lubricant that's present in the engines, they use this material as well. So we are thinking about all of those kind of softening materials as possibilities for our use in asphalt industry and how we can bring the stiffness of the recycled asphalt back down, right? Because this is, again, the critical thing. We want to reduce the emissions. We want to bring that stiffness back down. Can we use materials that already exist? So we know that proprietary rejuvenators work well, but these have a life cycle cost too. Instead, we want to use materials that already exist, that are naturally present, and that we can quickly soften our asphalt mix, get it below that appropriate mixing temperature so that the CO2 emissions are not too high and the human health is not in danger when we use those mixes. Now, one thing you have to be careful, of course, that it doesn't compromise performance. So anything we use here, make sure that it doesn't compromise performance before you do it. And finally, again, I want to talk about asphalt replacement, which is kind of what I was going for. We talked about it, obviously, using recycled asphalt, which is one critical way and probably the most critical way that's on the horizon, because we already know this material worked once, so we can recycle easily. That's perfectly fine. But now we want to know, how can we replace the asphalt with other materials? The first one that I think is most critical is, and I'm unique in thinking this is most critical, most people kind of overlooked it, but I think sulfur is a very good option, because sulfur, it's so widely available and we know that the performance is good. So in this paper that we did, we looked at the sulfur as a replacement for asphalt binder in the mix, and also for the asphalt aggregate. So you can add it by what they call wet method or dry method, right? Where you blend the binder with sulfur first, or you just blend the whole mix with sulfur and it's more like an aggregate. So we use these kind of elemental sulfur pellets, but the problem with sulfur is that human health hazards exist from this. So this material emits a lot of toxic fumes, and again, we have to think always of the health. So we did run some tests, these tests for rutting, for example, the deformation of the pavement, that's Hamburg wheel tracking test, and cracking test in the IFIT, Illinois Flexibility Index test. We found that the rutting improvements is generally improved when we add sulfur. Cracking is a little bit more mixed, but it's generally 30% sulfur didn't compromise it too badly, so we consider that a possibility. And what I like about this study is it just shows the feasibility that, yes, we can replace asphalt with something in big percentages, right? So besides recycled asphalt, nothing else right now we're using more than 10%. But sulfur, we can go up to 30%, for example, and make it. And this leads me into the kind of closing I want to make here, which is talking about the new technologies. So for example, here's plastics and asphalt. And actually, India is a world leader in this area. Many cities right now, Chennai, Pune, and I apologize if I'm saying those wrong, but these are cities that are already using plastic waste due to a mandate from the government. And this plastic waste is now being used as a replacement for both, again, asphalt binder and aggregate. So, but the disadvantage here is that the waste needs processing. It's not ready to go into asphalt. So for example, you have recycled bottles like this sanitizer, for example. You have sanitizer, and when that bottle's empty, I will put that sanitizer in the recycling, and somebody will take it to a processing plant to process the recycled material, right? Because it cannot just go in the asphalt like a bottle. So it's going to be melted down. It's going to have some depolymerization or some change in the structure and added to asphalt to make a mix. But those changes, structural changes have some disadvantages. They create some CO2 emissions themselves, and we have to be very careful that we are not compromising sustainability when we do that, right? So this is very critical. This is something we always want to keep in mind when we're using plastics, is that we cannot spend too much energy recovering them. So there's two methods, as I mentioned. Dry method. This dry method means you're going to add just the pieces of waste plastic like an aggregate, right? And bind them with the normal asphalt binder. The second is wet method, where you're actually going to blend the plastic with the binder, and then you're going to use that as their whole binder. And that's the more attractive method if we can make it work, because we replace the asphalt binder, which is the part that's really contributing to global greenhouse gas emissions the most. Another option is the ground tire rubber. And again, excuse me, I think this will be so critical for India, because as many vehicle tires are wearing out, many more people are driving right now. The highways are really increasing in their traffic factor. There will be a lot of leftover tires available. And when we grind that tire rubber, that can be available through, again, wet and dry methods. And we know this works, right? Rubber is a good material because it's heavily elastic. So we know that when there's a strain or a stress applied to the pavement, that deformation or stress can easily be recovered because the rubber is very elastic material. So it's not like the binder, which is viscoelastic, which is a little bit more between solid and fluid. Rubber is a very stiff elastic material. So we know it works well. But again, one of the major challenges here is that first of all, we have to process it. So that takes time and energy. And second, and most importantly, it needs to be stable. So it needs to actually disperse well, which rubber and many plastics do not have a fundamental compatibility. So this is where I'm hoping the next generation of researchers, all of you guys, will pick up this issue on how to make these more compatible and use these in high amounts. And maybe one day we'll be driving on roads entirely made of plastic or entirely made of rubber rather than asphalt, which will be in part a sad day because it's such a long legacy, but also will be, I think, very critical. So with that, I wanted to go ahead and wrap up. I think I've gone about 20 minutes. So I wanted to go ahead and wrap up and have some time if anybody has any questions. So thank you so much for your attention, and thanks to all sponsors of this work.
Thank you very much, sir. Thank you very much for your time. Yeah, students, if you have, there is a question in the chat box. One participant have raised a question. Hello. So they were asking recycling of old flexible materials to reuse is ultimately save money, but how to get same quality as per requirement?
Yes, this is such an important question, and this is the biggest focus, right? Because if you use a recycled material, and let's say that recycled material doesn't perform as well as the original one, then maybe you'll have 5 years of life of pavement instead of 15, right? And if you go and have 5 years of life of pavement, and you have to do that 3 times the same construction. So actually, this is going to be more greenhouse gases. This is going to be worse for you, right? You need to instead find only materials that are well compatible. So that's why I suggest, for example, compatibility tests, the test we proposed in the previous part of the presentation where I talked about titration-based procedures, very simple screening tests, inexpensive screening tests, but just to understand what you're working with, right? Because if you understand your material well, then you'll have no problem, you'll have no worry that it's going to fail prematurely. Now, if you know, like I said, that you have a wrap or a recycled asphalt that cannot be used, it's really too stiff, you can try to add something to it. For example, oils, I saw like rice husk, corn, soybean, all those kind of oils. You can reuse those to help regenerate some of your work. I think last time I presented for you all, I showed some work we did on Rejuvenators where we used a waste cooking oil. And the waste cooking oil can be used really in a nice way to rejuvenate those materials, right? We just have to make sure it's not costing any extra in terms of performance, because if it's compromising performance, we cannot use it.
Thank you very much for addressing that question, sir.
Uh-huh.
Yeah, any others? Any other? Yeah.
Yes. Sir, firstly,
Oh, sorry, go ahead.
sir, can I just proceed with my question, sir?
Yes, please proceed.
Yes, go ahead.
Yes, sir. So firstly, the presentation was really mesmerizing and it was very influential, sir. And my question is that sustainability has been the most trending situation now. So when we take asphalt pavements, is it sustainable when compared to other pavement types, sir? For example, if we compare these pavements with pervious concrete pavement or something else, there we can reduce the water runoff and we have a solution for reducing the emissions as well. And can we have such advantages in this pavement as well, sir?
Yeah, thanks. This is a really good question. So I will say that there are always advantages and disadvantages. So first of all, we do have also what we call porous asphalt. I didn't talk about it in this presentation, but we do have the option of porous or permeable asphalt as well to reduce the water runoff. So it's not good for high traffic, but we can use it in some low traffic applications. Now, second, and maybe more importantly, I think we have to always evaluate the individual requirements of a specific project. So if you have a very heavy traffic with a lot of traffic and a lot of large trucks, then concrete usually will end up being more sustainable because you'll have a better long-term performance, right? So even though concrete has a lot of upfront costs, because to produce Portland cement, you have to heat to maybe 1200 degrees Celsius, extremely high temperatures, the input products, and you have to produce those. So it will have a very high upfront cost in terms of sustainability, but you might get a much longer life, 20, 30, 40, 50 years. But you also have to account for what kind of distresses might be present. So for example, in Portland cement, a lot of times you need reinforcing steel. But if water can reach that reinforcing steel and cause some kind of damage to that steel, you might end up decreasing the life of your pavement quite a bit. So you always have to keep in mind what are the circumstances. Is it a high traffic? Is it a low traffic? Is it a wet area? Is it a dry area? Is it going to be cold? Is it going to be hot? And all those things have to come into consideration. So that would be my answer to how you would choose. It's on a case-by-case basis every single time, and only you can do that evaluation. Another issue that I should mention is availability of raw materials. If you have to transport the cement for a long time, this is going to cost a lot of energy to keep it heated, moving in the truck, and to move it. Same thing with asphalt. So you sometimes just have to use what's nearby. Same for aggregates. Sometimes you only have one specific source nearby and you have to use that. So all of those things, I think, factor into the choice. And I will never say one's better than the other. I work with asphalt more, but I will never say one's better than the other. It's just depending on the situation. Hopefully
Yes,
that
sir.
answered the question.
Yes, sir. It was answered, sir. Thank you, sir.
Mhm. Anything else? I think probably now everybody's ready for the dinner and to celebrate the festivals. So
Yeah. It's celebrating the festival.
yeah. So well, thank you all so much. For the opportunity
so
to
much.
present. It was really wonderful.
Thank you very much, sir. Please think of about my proposal that we were discussing way back. Yeah, hello.
Adding to it, I just have one more question, sir. If
Sure.
you, yes, sir. So, like, we have been hearing that 3D printing systems have also been in use. So, can we use such type of technology for paving these type of pavements, sir? And will it be suitable?
Yeah, this is a very good question. The 3D printing is something really interesting. So with 3D printing, it's going to depend on how fast the materials advance, because I think the materials right now, it's very hard to print at a large scale. So remember, pavements are a very large scale problem. So I think yes, in down the line, once we figure out a way to scale this and make it so we can 3D print maybe hundreds of kilometers of pavement at once, then we can do it. But I think at the time, right now, it's not an option yet. So, but I think it will come. I think it will come in due time, and I'm excited about the prospect of 3D printing in pavements for sure. I think it's an interesting topic for the future, and I suggest if people want to work on it, this is a really exciting area.
Yes,
thank
sir.
you very much.
Thank you, sir.
There is one question.
Okay, yes, I see the question. The question says how to model asphalt pavement as viscoelastic material and ANSYS APDL. What inputs will be required for modeling it? So actually, to be honest, I'm not very familiar with ANSYS software. I use always Abacus when I did finite element modeling. But usually what you need is some experimental test. So usually you will test the material first in some experimental procedure, and you will find some small strain behavior. So you will test a sample of the pavement material, in this case asphalt mixture, and you will just do some tests in the lab to find the properties, and then you will find whatever your finite element engine tells you need to input. So it will say, for example, creep test or dynamic modulus test, whatever that test is. You'll just run that in the lab, and then you will get those inputs. But to be honest, I'm not familiar with that software, so sorry about that. I always use Abacus, which always wants the Prony series coefficients, we call them, and that's coming from those inputs.
Thank you very much, sir. Let us go with the next thing. Thank you very much for your presentation and acceptance for the second time we did. Thank you very much, sir.
Absolutely, you're welcome, and great to talk to you, and we'll keep in mind for the future. Yes, so we'll talk to you soon.
Yes, thank you. Yeah, please proceed, Krishna.
Okay,
Yes, sir. Thank you, sir, for such a glorifying talk and sharing valuable assets of knowledge with us. Also, I would like to express my deep gratitude for all your support and cooperation with the Department of Civil Engineering SPECW. Once again, thank you for your time and consideration towards ScTACE 2021. Finally,
okay.
it's time for us to bid parting for the day 2 and let us meet tomorrow at 9 a.m. for the final prime of ScTACE 2021. Before I conclude today's session, I would like to convey my sincere appreciation and gratefulness to the speakers and audience for making day 2 of ScTACE 2021 a successful one. Let us meet tomorrow with much embrace zeal for new learning and wishing you all a great evening. Thank you.
Thank you very much, sir. See you soon. Thank you.
Yes, thanks everyone. Bye, and feel free to email me with any questions.
Sure.
Bye, everyone.
Bye.